Thank you so much. I'm Becky Dawson, and I'm excited to review what our field is learning about establishing the architectures of planetary systems. Planetary systems exhibit a surprising diversity from the solar system, which has our rocky planets closer to the sun and giant planets further out, to giant planets like hot Jupiters, which orbit extremely close to their host star, to gas giants at or beyond 50 AU, to compact, tightly spaced super-Earths and mini-Neptunes. A planetary system's orbital architecture refers to the observed combination of individual orbital properties like eccentricities, relative orbital properties like spacing and coplanarity of planets, and position and morphology of debris belts. We had a very simple blueprint for the solar system's architecture that began with a cloud of gas and dust that's spinning and collapses into a disk. Then further out in the disk, where there are ices available and large feeding zones, a core can form and accrete a gas atmosphere to become a gas giant. After a few million years, the gas disk goes away and rocky planets form in the inner system. And we're left with an expected architecture of rocky planets close to the star, gas giants further out, and debris at the edge on circular orbits and with planets orbiting in the same plane. However, not all planetary systems share this expected architecture. And that means we need a new blueprint for the origins of planetary systems that take us from the formation conditions to the different physical processes they trigger and that lead to the diversity of orbits and compositions that we observe today. What we currently have is not really a blueprint, but a bunch of theories and lively debate over them. I was going to describe it as a cookbook, but a cookbook doesn't usually have a bunch of recipes for the same thing. So it's more like allrecipes.com, which has almost 1 million recipes, including these two for ravioli. The first one warns us not to be intimidated by the large list of ingredients, and the second includes store-bought ravioli as one of the ingredients. Either of these could be great in our pandemic times. I recommend the first one if your ballroom dance lessons and happy hours have been canceled and you're looking for something to do. The second one might work better if it's your toddler's daycare that was canceled. So how can we determine how the ravioli was made and why some systems have ravioli and others have hamburgers? We now know of thousands of known exoplanets, and this gives us both population demographics and great detail on some individual systems. So today I'll review how, in our quest to create a blueprint for the origins of planetary systems, individual system architectures complement what we learned from population demographics. I'll first speak about short period planets such as hot Jupiters and hot Neptunes. These clearly do not have the expected architecture. So what are we missing or getting wrong in this framework? There's been several types of theories proposed for the origins of these short period planets. One is that despite our expectations, they might be able to form in situ very close to the star. Another is that they could form further out, like where we think our own Jupiter did, and migrate in through interacting with the protoplanetary gas disk. A third is that they may, after the gas disk goes away, be disturbed onto a very elliptical orbit and go on close passages to the host star that lead to tidal migration. So we'll now talk about how combining demographics with detailed individual architectures of particular systems are giving us some clues over which of these mechanisms are at work. And I'll first show you some evidence that there may be multiple of these channels at work in the origins of hot Jupiters. So this first piece of evidence comes from whether hot Jupiters have other planets nearby in their system. Population demographic studies have taught us that most hot Jupiters lack nearby companions, making them very different from other types of planets. And this is very consistent with that tidal migration scenario, because as a giant planet's tidally migrating, it would wipe out or eject any other planets along the way, leaving it all alone. However, there's at least one system that is different, WASP-47b, and has two nearby companions. So this is telling us that even if tidal migration is at work in creating many hot Jupiters, there are at least some coming through another mechanism, which may be disk migration or in situ formation. Hot Neptunes turn out to have some things in common with hot Jupiters. They're also lonely. So we see on the plot on the left of planet radius versus orbital period of Kepler planets characterized with Lamos, that the planets in the pink box, which this paper is considering hot Neptunes, also tend to be singles rather than observed in multi-planet systems. Then individual architectures are telling us something consistent here. So recently with Gaia, we and other teams have been able to characterize the mutual inclination between a hot Neptune in the Pi Mensae system and a further out giant planet, and found that there's a significant mutual inclination of about 40 degrees or higher. And this would be very consistent with triggering high eccentricity tidal migration. However, the big difference from the hot Jupiters that I talked about is that for these hot Neptune systems, we don't know whether there's other planets in the system that just aren't transiting because they have significant mutual inclinations. And that could also be consistent with the Pi Mensae system if that outer planet has disturbed mutual inclinations of a multi-interplanet system. So in the case of hot Neptunes, it's not as clear that it's definitely tidal migration causing these trends. It could still be in situ formation or disk migration. So now I'm going to take a pause to talk about a special type of configuration called orbital resonances. So orbital resonances can occur when there's integer period ratios between bodies in the system. Really famous example is Io, Ganymede, and Europa in our solar system. And because of the integer period ratios, the planets repeat their conjunction at the same spot. Orbital resonances get captured when there's some sort of dissipative process at work, like migration or some sort of planet disk or tidal interaction. So if we see this in a system, we know that there's been some sort of dissipative process at work setting up this resonance. So integer period ratios can make it possible to have an orbital resonance, but to technically have an orbital resonance, you need to look at a special angle called the resonant angle that involves the positions of the planets and or the periapses, like where they have their closest approach to the star. You need to check if that angle is tightly oscillating around a particular value instead of sweeping through every possible value. That's when you're technically in resonance. So throughout this talk, we're going to take a look at some resonance systems and see, are they actually in resonance or do they just have these integer period ratios? So now let's go back to giant planets close to their star. If we look a little bit further from the star at warm Jupiter, so maybe 10 to 100 day orbital periods, there have been observed to have some that do have integer period ratios. So here on the left, I'm showing a plot of planet mass versus period ratio, where the red shaded regions are places where there's integer period ratios between the planets. And giant planets seem to be, at least in the radial velocity sample, even more likely to have these integer period ratios. However, we need to look at individual systems in detail to characterize whether they're actually in resonance. So recently we've been able to look in great detail at the TESS TOI 216 system of two warm large exoplanets using a combination of radial velocity TESS and ground-based transit. And with the new precise characterization, we can characterize that resonant angle and the eccentricities in the system really well. And surprisingly, it looks like that the system is in resonance, but that angle, which you can see in the top panel, has a rather large oscillation amplitude. It's not what you'd expect just from nicely migrating two things into resonance. And one of the planets has a pretty big eccentricity. So this could be a system where there was not just a gentle migration history, but some sort of kick, maybe two planets migrating into another planet that formed in situ or something like that. So let's now move on to wide separation giant planets at 30 or 50 or even 100 AU. These planets, we also debate their origin. So here's a diagram that's kind of similar to the one I showed before of how you could get a giant planet out at 50 AU. One possibility is that it formed more like where our own Jupiter did and then got scattered out by another planet or underwent multi-planet disk migration with another planet, which could move you out instead of in. Alternatively, it might be able to form all the way out there, either through modifications to what we know about core accretion, gravitational instability where the disk fragments, or cloud fragmentation, which is how we think that stars form. So a lot of people have framed this question, are these really planets or are they more like mini stars? And again, population demographics and individual architectures are giving us some evidence for what's going on. So population demographics, this system that I am showing in the corner, HR 8799, was one of the first system of directly imaged planets. But now direct imaging surveys have been looking at more and more young systems and finding that as they push closer to the star and to smaller, lower mass giant planets, the occurrence rate picks up. And that's more consistent with the expectations from core and pebble accretion than from gravitational instability. An individual architecture that weighs in on this is the HR 8799 system itself, that one in the top left corner. It's a system of multiple giant planets in or near orbital resonance. So it really looks like a planetary system. So these things together suggest that these wide separation directly imaged planets, or at least a significant portion of them, may be more an extension of the giant planet population like our solar system giant planets. Then the last population I'll talk about are the compact multi-planet systems of super-Earths and mini-Neptunes. Kepler-11 is a canonical example, which has a bunch of super-Earths and mini-Neptunes packed within the orbit of Mercury. And similar to the other types of systems we talked about, the origins of these systems are very much debated. For these systems, there are two popular classes of explanation. So as I walk you through these two classes of explanation, I'm going to do it with a cartoon. In this cartoon, we have planets forming in a young gas disk shown in green, and over time, which is going down the slide, that gas disk is going away. So in the disk migration scenario, we have these super-Earths or mini-Neptunes form further from the star, so on the right side of the slide, it's further away, and then migrate in while there's still a gas disk around. And this is thought to often lock planets into an orbital resonance configuration. An alternative is that these planets may have formed more like the planets, terrestrial planets in the solar system through giant impacts. So in that scenario, planetary embryos would grow and merge and collide. And if they manage to grow large enough while there's still gas around, they may be able to accrete a low mass envelope and end up like a mini Neptune. So in this case, they'd form very close to where we see them today. So now let's look at how some population demographics and individual architectures can help us test these two different ideas. So first, we're going to take a look at orbital resonances again. So now on the left, I'm showing a histogram of orbital period ratios of Kepler planets. And you can see that this is a very wide distribution. Not all the planets are piled up at resonances. And so this might be a little inconsistent with our most naive expectation from disk migration, which might easily capture planets into resonance. So there's been a lot of work on why these planets, if they came from disk migration, aren't in resonance. And people in particular have been looking at, can the resonances break or go unstable after the fact, or different mechanisms for avoiding capture into resonance. Then from the individual architecture side, we have, even though most compact multis are not in orbital resonance, some are, and some of them have been extremely well characterized so that we know that resonant angle and we know the eccentricities. And I'm showing in particular some example of systems with resonant chains, so there are multiple consecutive planets in orbital resonance. So this is pretty easy to explain with disk migration, but how about in situ formation? How does in situ formation square with having this wide distribution overall, but then a few systems where planets are tightly in resonance? To address that, we've recently been mining our simulations of in situ formation to see if any planets just naturally end up in resonant chains. And we found that they actually do sometimes, at a rate that's consistent with what's observed when we take into account Kepler selection effects. So on the left, I'm showing an example of, on the top three are those resonant angles, and you can see them lock into resonance over time. So that instead of sweeping through every value, they start to tightly oscillate. And you can see eccentricities are being damped by a little bit of gas that's still around, and planets are settling into their final masses and orbital period ratios. So this is just one of a bunch of in situ formation simulations, but it ended up just happening to produce a resonant chain of 6 planets. We've also been looking at matching those detailed properties of observed systems like TRAPPIST-1. So on the right, we have an example where we have the planets in the TRAPPIST-1 system very close to where we see them today and locking into resonance through interacting with the gas disk, but without any extensive migration. So when it comes to resonant systems, the jury is still out. It's possible that either they arose through disk migration, which is more expected, or that they're an uncommon but perhaps consistent with the observed rate outcome of in situ formation. And it's possible that both of these can lead to that overall wide distribution of orbital period ratios where most systems aren't in resonance. So then a final type of trend that I'll talk about for these compact multi-planet systems is how similar or different are these planets. So we know from the population demographics that there's a lot of diversity if we look at the overall population of super Earths and mini Neptunes. I showed you how they have that very broad distribution of orbital period ratios. We see a lot of diversity in some of their orbital properties, and we see diversity in their compositional properties as manifests in this plot on the left of the mass-radius relation. There's, at a given mass, a planet could have a very different radius from one in another system. So this suggests a lot of compositional diversity. Meanwhile, in individual systems, there's evidence, which we'll hear more about in the next talk from Matthias, and there's also been a lot of work done, that within a single system, we see in this plot from Weiss et al., planets arguably tend to have the same sizes and spacings as each other, even though it's quite different from system to system. So there's a lot of work being done to explore this, but I'll present you today with one possible explanation, which is that planetary systems may have different formation conditions. So now I'm bringing back this in situ formation cartoon. On the left is the one we looked at before, where planets are able to form while there's still some gas around. Whether that can happen is going to depend on how many solids are available in the region where the planets are forming. Probably these solids have to be brought in from the outer disk. If there are fewer solids available, then the planets have to wait to undergo their formation until after the gas disk goes away. Then they can end up with rocky compositions, and they also end up with more widely spaced, mutually inclined, and elliptical orbits that aren't captured into resonance. And these differences persist even as the systems evolve for billions of years. So systems can look quite different depending on the formation conditions. Recently been exploring how this manifests in those different observed trends that I just talked about. So on the top, I'm showing a plot of the distribution of orbital period ratios. Having a range of formation conditions can give us a range of different period ratios when we look at the population overall. And it can give us diversity in composition, which I'm showing in the bottom left plot. There's a lot of scatter in the mass radius relation in systems forming under different conditions. And then finally on the right, I'm showing individual systems. And within a system, planets tend to look similar and have similar spacings, even though the planet formation process is quite stochastic and can involve losing atmospheres. Overall, the formation conditions are kind of setting what the system looks like in terms of spacing, sizes, etc. So this is one explanation, and I would say the jury is very much out on the in situ formation versus disk migration debate, and it's going to be exciting to explore this further so that when we look at a system like Kepler-11 or TRAPPIST, we can know, did those planets form close to where we see them, or did they form much further out and migrate in? So there are some now exciting future prospects for creating a new blueprint for planetary systems. There are going to be a lot of really interesting talks about this on Friday, so I'm just showing a few examples now. We'll be able to expand the parameter space of known planets with future microlensing missions, and that's sure to reveal more interesting and intriguing demographic trends. There will be upcoming missions doing more atmospheric composition, which will be really interesting in trying to link the atmosphere properties to the architectures in that system and see if it tells a consistent story about the formation. Then a final exciting thing is that there are new missions and surveys coming online that are going to let us look at individual systems with a much wider view. So systems where right now we may only know about the small planets close to the star, with Gaia, with better radial velocity follow-up, with more bright transiting planets, we'll be able to scope out more of the full system and see, just like we do in the solar system, how the different pieces tell us a story of the origin. So this is a completely made up system where I'm kind of envisioning what that could look like. This is a vision of like what we might see with a future giant space telescope. So this is a system where we have a planet in the habitable zone, and all the other pieces of the system tell us about that planet's history and habitability. So we have it near the inner working angle, a shepherded debris ring that tells us some limits on the mass of the planet. We see that there's 3 compact planets in an orbital resonance with very water-rich composition, that there's a gap between them and the outer belt that might suggest that they migrated a little bit. Meanwhile, there's a Jupiter on an elliptical orbit that's been characterized using radial velocity in Gaia. It's causing an offset in the debris ring, and it may have played a role in delivering water to these water-rich terrestrial planets. So it'll be cool to be able to do things like this for other solar systems. Then finally, a quick advertisement. If you want to think more about how connections between planets and stars inform us about their formation and evolution, please consider coming to this online conference from August 26th to 27th, hosted by KITP. It's all online and you can register for free. I'll leave you with this summary sentence. Thank you very much.